We're all constantly trying to guess what's next. Will it rain on my day off? Is our team going to win the championship? Will this big project actually hit its deadline? We're always trying to get a handle on the future. So today, let's learn how to stop just guessing and start really understanding uncertainty.
And that's really the big question, isn't it? How do we go from a gut feeling to having a real solid way to look at what might happen? How do we build a system for it?
Well, the answer is kind of simple, actually. It all starts by learning to speak the same language. See, before we can analyze chance, we need a really precise way to talk about it. So for the next few minutes, we're going to learn the basic vocabulary of this powerful new language, the language of probability.
Okay, so the very first word in our new vocabulary is experiment. Now I know, it might sound all scientific and complicated, but it's actually the starting point for everything else we're going to talk about.
The official definition says it's a process that generates raw data, which, let's be honest, sounds a little dry. So let's break that down. Just think of an experiment as any action we decide to watch, where we're just waiting to see what happens, what data it gives us.
And that's the absolute key. If you know exactly what the result is going to be, it's not a statistical experiment. It's the not knowing, the uncertainty, that makes it an experiment in the first place. And you can see just how broad this idea of an experiment really is. It can be something as simple as tossing a coin to see if you get heads or tails. But it can also be something way more complex, like launching a missile and recording its speed. The thing they have in common? They're both actions that produce some kind of data we can look at.
All right, so once we've picked our experiment, what's next? Well, the next step is to map out every single possible thing that could happen. We need a complete map of all the possibilities.
And this map has a name. We call it the sample space. It's just the complete list of every possible result. I mean, everything. Not just the outcomes you're hoping for, the ones you think are likely, but all of them, no exceptions.
So let's stick with our simple die rolling experiment. If that's the action, then the sample space is just 1, 2, 3, 4, 5, and 6. That's it. That is the entire universe of what can happen when you roll that die.
Now, for a sample space to actually be useful, it has to play by 3 really important rules. First, it has to be collectively exhaustive. That's a fancy way of saying nothing gets left out. Every single possibility is on the list. Second, it's mutually exclusive, meaning you can't get 2 outcomes at once. You can't roll a single die and have it be both a 2 and a 4 at the same time, right? And finally, finest grain. This just means we break it down into the smallest possible pieces. So rolling an even number isn't a single outcome. The finest grains, the distinct outcomes, are 2, 4, and 6.
Okay, so we've defined our experiment. We've mapped out every single thing that could possibly happen in our sample space. Now we could finally start talking about the specific results that we actually care about.
And that brings us to our next word, event. In day-to-day life, an event is just something that happens. But in probability, it's very specific. An event is just a piece, a subset of that whole sample space that we're interested in.
Let's go right back to our die. Let's say we're interested in the event of rolling an even number. Well, we just look at our sample space and pull out the outcomes that fit that description, 2, 4, and 6. That little collection, that group, is the event.
And we could even break this down a little more. If an event has just one single outcome, like rolling a 4, we call that a simple event. But if it's made up of a bunch of outcomes, like rolling a 4 or higher, which includes 4, 5, and 6, we call that a compound event. It's really just a few simple events bundled together.
So we've covered experiments, sample spaces, subsets, and events.
Okay, now for the really cool part. Let's connect all this to something you probably ran into a long time ago in math class.
Just think about it for a second. We have this big overall container of possibilities, and then we're pulling smaller groups of possibilities out of it. A large, universal set with smaller subsets inside it. Does that ring any bells?
Because here it is. This is the aha moment. The language we're learning for probability is built directly on top of the language of set theory. It's like a direct translation. What mathematicians call a universal set, we call a sample space. An element in their world is an outcome in ours, and what they call a set, we call an event. It's the same idea, just with new labels. So here's the kicker. If you understand the basics of sets, you're already halfway to understanding probability.
So you might be sitting there thinking, okay, that's a whole lot of definitions. Why do we have to be so particular? Why do we need this formal structure for everything? And that is a great question.
Well, it's because this foundation, this language, it's everything. It removes all the guesswork and all the ambiguity. When someone in this field talks about an event or a sample space, everybody, everywhere, knows exactly what they mean.
This shared vocabulary is what lets us move past just guessing and actually build the tools to systematically analyze the uncertain world around us. It's the bedrock for all of statistics.
And that's really what I want you to take away from this. These concepts, experiment, sample space, event. They might seem almost too simple, but they are incredibly powerful. Every single complex statistical model you've ever heard of, it all starts right here with these basic foundational ideas.
So, we've got the grammar. We've learned the basic words for talking about chance. So the next obvious question is, what can we actually say? How do we use this new language to figure out how likely an event is to happen? Well, that is a great question for our next explainer. Thanks for joining me.